Right, let's continue with lecture 1. This slide is related to probability function. So officially, I now introduce you to probability function. I already talked about each part of these components before, but anyway, you can go through it to see now what do we mean by probability function. And here you see, for example, probability of event A more than equal 0, because here are the axioms that we need to show, for example, this is a probability function. And don't forget that there should be an upper limit for probabilities. Like this one cannot be more than 1. So as I explained before, it should be a value between 0 and 1. And I personally prefer to even include that inside these axioms. But anyway, here also mentioned that the probability of omega, which is the sample space, is equal to 1. The probability, of course, of universal set, which covers everything, is equal to 1. And from here, we understand that PA should be a value between 0 and 1. Okay, now about the term mutually exclusive, it means that disjoint events. So here, whenever this is the case, whenever this condition holds that A and B are disjoint, then we can say that probability of A union B is equal to marginal probabilities. Why do I call them marginal probabilities? I will explain when I tell you about probability distribution, but this is the case. Like when they are disjoint, like this picture, they don't have any intersection. Their union is their summation of marginal probabilities, the single events for each one of them. So whenever there are intersections like this, there are some common elements, then this is not true. This formula, so not always hold. Only when they are disjoint, and I explain it in the next slide. And let's go through probability of union of events that I mentioned. Like when they are not mutually exclusive, for any sets that you can imagine, when we are talking about any A and B, doesn't matter this is mutually exclusive or not anyway, because this part is equal to 0 for case of disjoint events, right? When there is no intersection. So this part is 0, so you will reach the formula that I showed you in the previous slide. Here, you see? Okay. So this formula always holds for any two sets that you can imagine. Even for mutually exclusive, as I said, we don't consider this part, but anyway, it holds because it gives you 0. So whenever you want to find the union of two sets of events, of course, and here you say this is equal to their summation of marginal probabilities minus the probability of their intersection. Now, in this picture, that they are not mutually exclusive or disjoint events, let me tell why. Because first you consider this part, then for B, and as you can see, you are counting the elements here twice, the intersection part. And that's the reason we should get this one, subtract this one from the summation of the marginal probability at least once. And if the number of sets increases, the formula can be generalized, and we should change the sign again and again when the number of sets increases. But anyway, in two sets, it's easy to explain, and you can see why. And what about independent events? Students tend to confuse independent events with disjoint events. For disjoint events, we say that there is no intersection. Like this is A, by the way, it cannot be outside the omega. Yeah, this is A and this is B, there is no intersection. But when we talk about independent events, we don't show them in Venn diagram. So these diagrams, as you can see, we call them Venn diagram. I guess you already know anyways, but for independent events, we cannot show them like this. So what do we mean by independent events? It means that if I have an event A and B, the appearance, or for example, if A happens, does it affect the probability of B or not? For example, I know today is sunny. Does it affect the weather of tomorrow? Maybe yes, maybe no. There might be some probability. So these two events are not independent. Now, if I throw an unbiased die, it happens to be, for example, 2. If I throw it again, the fact that I know the previous one was 2, does it affect my next trial? No, it doesn't. So these two events are independent. So in that case, when it happens and I know that A and B are independent, you can find the intersection of A and B by using this formula. So this formula is not always true. This formula is it's not always true because A and B should be independent events. If this is the case, yes, this formula works. But if not, you cannot use this one. But the probability of union of events always work, okay? Just in case this one is mutually exclusive, as I said, this is 0, it doesn't affect the fact that this formula is correct. But for this case, for independent events, we should be careful that A and B, whenever they are independent, then you can say that the multiplication of their marginal probabilities will be equal to their intersection. So what can I say? I can say that two sets A and B are independent if and only if this formula holds. Okay, so it means that from here you can imply this one, and from here you can imply this one. Okay, so if I increase the number of events and I'm sure they are independent, like throwing a die or, for example, tossing a coin, these events are independent. And later you will learn about, for example, binomial distribution, and I will keep mentioning about the independent events also there. So in this case, as you can see, easily you can calculate the intersection of these events which are independent by using this formula. And we should remember that this condition only holds if they are independent. And conditional probability, which is very important. And in most of our daily calculations related to probabilities, we are dealing with conditional probabilities because our probabilities are depending on other events. So most of them are dependent instead of independent, which we could easily calculate by using the previous formula. So if that's the case, how can I deal with that? I mean, when I denote it by this, first of all, what does it mean? It means that the probability of A if B happened, you see? So if B happened, the second component here, it means that you are sure this event already happened. Now, what's the probability of A? Okay, so we use if such that or such notations for this. So what's the probability of A if I know B happened? And this one is different from intersection of A and B. That one means that A and B happen at the same time, but this is different. We are here asking what's the probability of A if B happen. And sometimes it's confusing, so we need to solve examples for sure to know exactly the difference. And this is natural if it feels confusing at the beginning. But let me show you how you can deal with questions related to conditional probabilities. So here, if I ask you, what's the probability of A if B happened? Or given B, sometimes we use this term, given B, such that, if B happened. So this is the simple formula, the simplest formula that you can use. But when can I use that? When I have the information related to these probabilities. If I can easily calculate them, then by using this formula, easily I can find. But unfortunately, sometimes it's not easy like that. Then we need to know about different theorems or maybe rules in order to deal with that. So let's go through them and I tell you how we can deal with such notation. But remember also, in case of independent events, we have such case like, what's the probability of A if B happened? Why this is equal to probability of A itself? Because A and B are independent. Okay, so in case of independent events, that's the case. If, for example, I throw a die and it happened to be 2, it doesn't have any effect on my next trial. In the next trial, again, the probability of receiving, for example, number 3 is 1/6. The probability of receiving 4 is again 1/6. It's an unbiased die. So you see that in the first trial, it doesn't matter what happened. When this is the case, when these two events are independent, then the probability of A knowing that B happened is exactly equal to probability of A. So as you can see also, we mentioned about the intersection, that you are allowed to use this formula only when those two events are independent. Great. So please go through this slide carefully. And let me also explain about that part, which is very important to solve the problems. Like if I know, for example, what's the probability of A intersection B, and I have the information related to marginal probabilities, it's easy to calculate either of them, this one or this one. But what if I don't have? Then I should use this formula. Let's say I want to calculate probability of B over A, and I don't have information of the intersection of this probability. Intersection of, I mean, A and B. So what should I do? Let's see how I reach this formula. How did I understand instead of this part, I can use this. So consider these two equations and make them equal with each other through this part. The intersection of A and B are common in both of these formulas, right? So I can say the probability of intersection of A and B is equal to probability of B multiply this one, right? So here is what I said. For the second equation, we can do the same. So probability of A intersection of B is equal to probability of A multiply probability of B given A. So because these two are equal, I'm allowed to use either of them for this intersection. And that's the reason, for example, when I want to calculate intersection of A and B, I'm allowed to use this one. And you may ask me, how can I memorize it for you, for example? Because for our exams are online, I mean, our homework exam, as homework exam. So you don't even need me to give you formulas. You already have the formulas. But if it was a face-to-face class and the exams were paper-based, then students asked me, how can I memorize them? How can we memorize them? So here, for example, BA. The second part happened to be always here, the part which is given. And that's the whole goal of conditional probability. Why is that? Because assume that you have a sample space. Here is B, for example, and here is A. So if I know A already happened, it means that A complement didn't happen. It's not possible that two events which are complement of each other happens at the same time. It's impossible. So whether, for example, the weather is 32 degrees or not, we don't have a weather which is 20, for example, 32 degrees or 0 degree at the same time. It doesn't happen. So here, when this happens, you are limiting yourself in this space. It means that this is your new sample space. And that's the reason, instead of considering your sample space here for conditional probability, you use the second component in this notation. That's the whole reason for that. So I'm interested in probability of B inside A. but not the intersection. That's why it's confusing for students. Like, okay, so what's the difference between intersection of A and B and conditional probability? So let's go through the examples in the tutorial to understand exactly the difference between these two. But anyway, here we are talking about limiting our sample space, then calculate this probability. So we don't consider these parts outside A anymore, like this part, even B here, we don't consider them. Okay. And for, as I said, when you want to calculate, for example, probability of B given A, you can use this formula. If you don't have information about this part, then you can use this formula. So you remember that second component should be here. If you cannot use this one, then by using Bayes' rule, you should use this one. Okay. And if, as I said, if you want to memorize, then not to forget, not, for example, calculating everything from the beginning. So you should interchange the place of them in order to put here. So you see the first component happened to be the second one and so on. Okay, the law of total probability. Why do we need this one? Let's go back to our main formula, or maybe I can mention here. Let's say I want to calculate the probability of B given A. So what's the easiest way to do that is to calculate the probability of B intersection A. Does it matter if I say A intersection B? No, the order doesn't matter because this is just an intersection. Okay, over P A, the second component, right? So this is the simplest way. As I said in the previous slide, sometimes you don't have information of this part, the intersection part. If you don't have that information, but you have information about the marginal probability of A, then you use the previous formula. But if not, if we don't have information of this and we don't have information of this one either, what can we do? Then we can use the law of total probability. Well, what does it say? It means that let B1 to Bk be a partition of the sample space, and Bi's are mutually disjoint. And let A be any event. So then you can consider this probability as, so this part is related to the previous slide, you already know. I here is just a fixed number there. But when we talk about PA, here we should consider a variable, J from 1 to K. It means those partitions. Let me show you here what we are doing. First of all, consider the partition that we used here. What do we mean by partition? It means that we have omega, the sample space. Now, I partition them into different sets for B. And if this is the case, and the whole thing assume that here is B, then I can partition them as disjoint events. Like, for example, this set doesn't interfere with this one doesn't interfere with this one. And what else? The summation of them should cover all the sample space, okay? So if I can do that, then it is possible to use this probability, because set A could be anywhere inside this omega. And one by one, I can consider this part. And you may say, how is it possible that I don't know about the probability of A, but I know about the probability of A given each one of these partitions? That's why, again, I need to give an example so that you get better ideas how it works. So to sum up for how to calculate conditional probabilities, whenever you want to calculate probability of B given A, whenever you have information of these two, it's easy to use this formula and you don't care about law of total probability or the previous slide. But if you don't have information about their intersection, then by using Bayes' rule, you can use this formula. And whenever you don't have information about either of them, then, for example, PA, if you don't have for sure, you should use law of total probability. There's no other way. So that's how it works, and we will practice that for sure in at least 3 exercises for our first tutorial in order to have better understanding for this part. If you feel any confusions during the lectures related to statistics at the beginning, this is totally natural because the tutorials are the most important. After seeing the exercises in tutorials, you will see that all of them are pretty easy to deal with. And if you have any questions after watching the tutorial, then you can ask me during that 1 hour that I will set for you weekly. Then you can ask your questions, or you can send me an email if you prefer using email instead of participating in those classes. Because for our online sessions, we won't take any uh, attendance, and also there won't be any new materials in those online sessions. So I would just answer your questions if you have any, and you don't need to participate if you don't have any questions for those sessions. So the announcements are also important. Please keep checking them. Before each Monday, I will post the videos related to tutorials and lectures. And as I said, you can use email or attend that online session to ask your questions. Okay, guys, see you in the next lecture.